calls me Lack, and what I'm going to be talking to you is about data analysis in the public cloud using Python. So the first question to ask, of course, is why would you want to do data analysis on the cloud? And part of the reason is because the public cloud infrastructure is extremely powerful. It's much more powerful than what you can ever have sitting under your desk. As I know a couple of points of to show you what kind of power we're talking about. 1 out of every 5 CPUs that are produced in the world are bought by Google. So in other words, 20% of every CPU that's bought, that's produced every year on year goes into the Google infrastructure. And that's in terms of the compute infrastructure. If you think in terms of networking, the amount of fiber behind the Google firewall is bigger than the rest of the internet combined. So if you're looking for the ability to scale up your data analysis, you need infrastructure that's extremely powerful, and you get that on a public cloud, right? Whether it's Google or Amazon or Microsoft, really the place to do data analysis now is to do it on a cloud because you want something that scales, right? The other aspect of it is that you need software that scales. And to kind of put this in perspective, many of you may have been using the Hadoop ecosystem, Hadoop, Pig, Hive, Spark, etc. Those all came out of the Google file system and the MapReduce frameworks that were, it was just white papers that Google published in 2002 and 2004. Doug Cutting saw it and implemented it as Hadoop. And that's basically led to the entire ecosystem of big data. But those are what we would call the first version of our big data stack. And the reason we call it the first version is that they're subject to one very bad issue. The issue is that you need to go ahead and create a cluster and manage that cluster of machines in order to run everything that you want to do. Okay. The second generation of Google, the big data stack, is this whole idea of scale independence. This idea that you basically have something that you want to run, and when you have to run it, you just lob it onto a cloud, and a number of machines basically processes your query, your job, whatever it is, and you don't actually know how many machines processed it. You don't own those machines. It's literally, you get a machine for seconds, right? We're not talking minutes, we're not talking hours, we're talking seconds. You just get a portion of those machines to get your job done, and then they go away. MapReduce is no longer used at Google. In fact, 2006 was the last project at Google that used MapReduce. Pretty much ever since then, we've been using these serverless architectures, and these that's what we're externalizing as BigQuery, as PubSub, and as Dataflow. But I'll also talk about Dataproc because it lets you take what it is that you're currently running, the Hadoop jobs that you're currently running, and bring it to the cloud. We think of it as a stepping stone to the more transformative things like BigQuery and Dataflow that might come later. Okay. So let's start talking about MapReduce and Dataproc and how you would use them. Okay. First of all, what exactly is MapReduce? It is this idea that you have some data set, big data, that is so large that it cannot fit on a single machine. And if that's the case, the way you kind of solve it is to basically take that data set and split it. And that's what you're seeing here with the input files. You're taking these input data and you're splitting it into split 0, split 1, split 2, etc. And you're storing it on different machines. So you're co-locating the data with the compute. And then you have all of these compute nodes processing their local data and writing their local result. Those are the intermediate files. And these local results are then combined in the reduce phase by another set of workers to basically go ahead and do the job. And it turns out that a wide variety of data analysis tasks can be separated into this map phase, which happens on parts of your input data, and your reduce phase, which kind of aggregates all of those results. And that's basically led to this plethora of MapReduce applications out there. And so you basically have this very rich open source ecosystem that's come around for doing big data. You have Hadoop, which basically lets you write MapReduce jobs, but it's very low level. So people created Pig, which is a scripting framework, or Hive, which basically places a relational database structure on top of your big data. And of course, Spark, which gives you an in-memory data set to speed up some operations. But with all of these things, right, you're essentially going to go ahead and create a cluster, and you're going to do everything on it. And so you could do this in Google Cloud, and I'll do a demo. And the demo that I'm going to be doing here and the rest of this talk is basically going to be assuming a single problem. And the problem is this. Imagine that you need to predict whether a flight is going to get delayed or not. And the idea is that you're sitting on the tarmac, the flight's about to take off, and you want to predict whether when it lands at your arrival airport, is a flight going to be late by more than 15 minutes. The idea is that if it's late by less than 15 minutes, you don't mind. But if it's late by more than 15 minutes, you need to do something. And you need to do this probabilistically. So we want to say that if it's likely to be delayed by more than 15 minutes, by more than 30%, more than a 30% likelihood of being delayed, then we need to cancel a meeting, we need to postpone a meeting, do something, right? So the idea is that we need to estimate the likelihood that the flight arrives greater than 15 minutes late. And to do that, we could do logistic regression. So let's take two input variables, the departure delay of the flight. So the flight's about to take off, and it was supposed to take off at 8 o'clock, and it's taking off at 8:20. So you're 20 minutes delayed. So that's your one input variable. And the distance that you need to travel, the idea being that if it's a very short flight, you can't make up a 20-minute delay. But if it's a flight that's 15 hours long, then you probably can make it up. So those are your two input variables. And that's what we want to do. So to do that, first thing that we need to do is that we need to start a cluster. Remember, this is wave one. We still need to think in terms of clusters. So I'll go ahead, I'll go to Dataproc, and I'll basically say that I'll want to go ahead and create a cluster, a Dataproc cluster. So I'll say I want to create a cluster, and the cluster that I want to create, let's say I want to create one with 4 CPUs, etc. Set up a whole bunch of things. I'll create it. It takes about a minute to create this cluster, which is really, really fast, as it turns out. But it is still a cluster that I own, that I manage. And meanwhile, so while the cluster is starting up, let's go look at the code that we want to run. The code that we want to run is logistic regression. And so I'll be using Spark. Okay, so I'll go ahead and set up a Spark context. And in my Spark context, I'll basically go ahead and read my data. And the data that I'm going to read is a departure delay, the amount of time that it took to taxi out, and the distance that we're going to be traveling. And then I'll use a logistic regression, and LBFGS is basically the optimization algorithm. I'll train it based on the flight's data, right? And I'll basically do that, and I'll go ahead and say that we want to cancel our meeting if the probability of on time is less than 0.7, right? So that's basically our threshold. So in my logistic regression model, I'll set the threshold to be 0.7, and I'll go ahead and I can save this model, right? So that's basically it. And then whenever I want to do a prediction, I will have a prediction for a departure delay of 36 minutes, where it took me 12 minutes to taxi out, and it's a 594-kilometer flight. And then I'll be able to predict, and it'll tell me whether or not I should need to cancel my meeting. So this is basically it. This is a typical Spark job using logistic regression, right? So at this point, the cluster one is done. And then I can go ahead and I can submit the job to this cluster. And to submit the job, right, it's basically, I will essentially say gcloud beta dataproc job submit to PySpark to this cluster one logistic.py, right? I can basically submit this job. I won't go through this. But once you submit the job, Spark is basically going to run, create my model, save it, and I'm ready to do my prediction. But the thing I want you to remember is that, well, I had my flights data on the Google Cloud Platform. So one of the things that you want to look at is in the previous thing, logistic.py, we were basically reading data off Google Cloud Storage. So that's the first thing that you needed to do when you have your data on the cloud. But notice that I didn't have my data on HDFS. I just had it on Google Cloud Storage, and Spark was able to read it directly. So that's one nice thing. You don't actually have to think about creating a cluster and putting your data on it. You just have your data on the cloud storage, which is very, very cheap. And then you can just spin up a cluster, submit the job to this cluster, and let's say the job is done. I can basically go back to this cluster and delete the cluster. And I would have paid for the few minutes that that cluster was up, but nothing more than that. Okay. But you're still starting and stopping clusters. And that's what we mean when we talk about this first version of the big data stack, this virtualized data center. Because whether you like it or not, you owned that cluster for those few minutes that it was run. That cluster wasn't doing anything else. You were paying for that cluster. You also had to manage that cluster. We kind of made it easier in that you did not need to put your data on HDFS, but everything else you still would have to do. If you needed other pieces of software, you might need to install it. In this case, I just needed Spark, so I didn't need to install any other software. But normally, you would be basically managing that software. So the idea is, how can we get to this point where we do not manage our clusters, right? So we could use Dataproc, which will let you do Hadoop, Pig, and Hive, and Spark, but you are still managing that cluster, even though Google will help you do it a little bit in terms of being able to read off of cloud storage, etc. So this is where we get to the second version of this data stack, this whole idea of a serverless architecture. And a serverless architecture is an architecture where you never, ever launch a cluster. Instead, you can just say, this is what I want to do, and I can do it. So to give you an idea, let's say that we want to use BigQuery. And BigQuery is this ability to run a SQL query. Okay, sure, I have a question. Okay, I have a question from Ardi. Yep. Yes, Ardi, go ahead. And does anyone have a question? Yeah, please ask Ardi, and he can type in the questions. Unfortunately, because this is a broadcast, I cannot hear audio questions. Okay, thanks. So BigQuery is this idea that you can go ahead and run a SQL query, right? And so let's go ahead and take a SQL query that we want to run. So here's basically, I have a data set in my cloud training demos from BTS, the Bureau of Transportation Systems in the US, and we have the flights data. And the flights data basically has the fields like arrival delay, departure delay, etc. So what I'm doing is that I'm basically saying, go ahead and select the departure delay, the average of the arrival delay, for every departure delay, right? So I'm grouping by departure delay, and I want to basically get the average arrival delay of it. So I can go ahead and I can run this query. And this query, I don't want to cache it. So run this query uncached. And as you can see, in 1.4 seconds, right? This entire table, so let's look at the table. Here's the table details. The details of this table. Okay, options. So here's the table, and this table is about 6 million rows. So we basically were able to go ahead and do our selection and grouping and everything, and we were able to do this processing in less than 2 seconds, 1.4 seconds. And notice that when I had to run this BigQuery, I did not actually start up any cluster, right? I did not start up any cluster. All I did was I said, here's my data in BigQuery. Now it could be in cloud storage. And I said, go ahead and do the SQL query for me. It's this nicely, it's it's quasi-relational data, so I could go ahead and do my select statement, and I could run it, and I just pay, in essence, for the amount of data that I'm processing. In this case, I processed 87.3 megabytes of data. I mean, the entire data set is 1 gig. It's not a very big data set. But I only process 87.87 megs because I'm only processing 3 columns out of that data set. This BigQuery is a columnar database. So you essentially are paying only for the columns that you're reading. So we are reading the entire data set, but you're reading only 3 columns out of it. So I'm essentially paying for those 3 columns that I'm reading. So that was BigQuery, and I ran it from the BigQuery console. But I can also run it from what's called Data Lab. And Data Lab is a Docker container that runs an IPython notebook. So you start it by saying Docker, right? And I'm basically going ahead, this is the name of it, GCRIO, Cloud ML Dev, Data Lab. And I go to my Data Lab, and there's my flights 04. So here, now that's my typical IPython notebook. And the package I'm importing, the Python package, is Google Cloud Platform.BigQuery. I can run that. And then I can go down here, and basically, that's my magic string, two percentages. So that's, and I'm asking for the schema of the BigQuery of Cloud Training Demos BTS flights. And that's my schema. So I have my flight date, unique carrier, airline ID, right? And I also have the destination. And in particular, I have the departure delay, I have the taxi out time, I have the distance, etc. And then, right, I can basically go ahead and write my select statement, the one I wanted to do. I can give it a name, departure delay query. That's my SQL. And then, right, so I run that, and that's all this does is that it stores this into a module called departure delay. And when I want to run it from Python, I say bq.query, BigQuery query, departure delay query, which is this name here, departure delay query. And then I'm converting it to a pandas data frame. So .2 data frame basically runs the BigQuery, takes the results, and converts it to a pandas data frame. So depth delay here is a pandas data frame, and I'm simply slicing it, right? So that's basically why. So now it's running, and about 2 seconds later, I basically get the first 5 rows. So minus 24 minutes. So these things are early, right? And that's the arrival delay and the standard deviation of the arrival delay. The reason being that if you're looking at a particular departure delay, so you're looking at all flights that departed 10 minutes late, and then you're looking at the distribution of arrival delays for them. So that's basically what I'm now doing. I'm plotting for every departure delay. I'm plotting the set of arrival delays, and that's what this is. So for a departure delay of 50 minutes, right, the arrival delays tend to range anywhere from 30 minutes to about 60 minutes. So that is that distribution there. Then what I need to do is now I can look at this distribution and say, I want to find a 30% likelihood. I can assume it's normal. So I can basically use a z-score and basically find the standard deviation, and then find the arrival delay. And then basically what I'm doing is, here's the departure delay, the mean of it. And this is where you have a greater than 30% likelihood of an arrival delay. And we want a 15-minute arrival delay. So that turns out to be about 12 minutes. So if the flight departs more than 12 minutes late, you have more than a 30% likelihood that it's going to arrive more than 15 minutes late, right? So that's basically a threshold then. We can tell people if you're leaving more than 12 minutes late, you're going to arrive more than 15 minutes late. That's our data analysis. And you notice that we could get this by doing a BigQuery query, right? I mean, we can write more complex queries, right, and so on. But that's essentially this idea that we have an IPython notebook, okay? We have a huge data set, and we're able to interactively query this data set. Although I'm showing you on 1 gigabyte, now the same order of seconds we can do on data sets that are up to multi-terabytes. So we can basically analyze multiple terabits of data using BigQuery, using Data Lab, and any query takes only on the order of 7 to 8 seconds max. And the reason it takes only that is that behind the scenes, we have hundreds of machines that basically you borrow for those 7 seconds, and then you're done, right? So it's like, notice that the main thing here is that it's serverless and it's auto-scaled. The bigger your query, the more machines you get. Okay. So, questions? Any questions? Andy, let me know if it's time, if I can move on. Yeah, if you have any questions, please ask, and Andy, you can type it up. Okay, I have a question. Can I write the result back into BigQuery? Absolutely, right? So you can basically do a query, you can take the result, and you can save it back as a table. And you can do that both from Python, and you can do it both also from the SQL query itself. You can basically say, save this result back into a table, into a view, and so on. Yes, you can do that in Data Lab. So as part of your BigQuery, the bq.query, there's here it is. Okay, BigQuery. Yeah, let's see. Okay, where is the I want the API doc. Yeah. Okay. Answer is yes. Yes, you can do that. And the libraries in Data Lab, they're already installed. So all of the things in that I am currently importing here. So in Data Lab, I was importing Matplotlib, TensorFlow, Pandas, NumPy, and BigQuery. All these are already installed. So I did not actually have to install anything. These particular ones are installed, and you can install other ones by simply doing %bang pip install. So you can install other packages as well, but these particular sets of packages are already installed. Cool. Any other questions? Any other questions, or can I move on? So one thing to remember is that the way BigQuery works is that you can write an entire table at once. So that's typically what happens. Okay. Is there a big difference between first generation and second, apart from convenience? Well, I mean, here's the thing, that you shouldn't downplay the convenience. Any Spark job typically takes things that often on Spark take hours, you can do in BigQuery in seconds. And so that often means that you can basically change from something being done on batch, right? So you do it every weekend and you publish a report, to making it a dashboard that the users can come in and do it very interactively, right? So the convenience is incredible, because now you're basically saying, remember that, okay, and the second question is there a cost difference? So that's another interesting thing, right? Economically, right? Whether you're running 10 machines for 1,000 minutes, right? Or 1,000 machines for 10 minutes, it costs us exactly the same amount of money, right? In our public cloud, we have thousands of machines, so it's not a problem. So you can take 1,000 machines and you can run them for 7 seconds. Or you can take 7 machines and run them for 1,000 seconds. It's going to cost you exactly the same. Might as well get your result in 7 seconds, right? So that's essentially where the economics here come in. Obviously, if you are running it at your company, you can't afford to have 1,000 machines devoted to doing your query processing. But we can, because we have hundreds of thousands of users who are all using this. Okay. So the answer is no, there is not really. No, there's a little bit of a increased overhead, but it kind of makes up for it. And so the economics that you have to remember is that 1,000 machines for 10 seconds is the same as 10 machines for 1,000 seconds. And that's kind of why all of this works. It works at scale. It doesn't work if you have a very small cluster. Okay. So the next questions, are there big differences? I answered that. Okay. Okay. What is the interface of data from local machine and from cloud machine? Is there any difference? Okay, all this assumes that you're storing your data on the cloud, right? If you are storing your data locally, then yeah, you're going to have to pay networking costs, and that's not fun, right? But the assumption is that you've decided that you're going to do things on the cloud, and you have your data in the cloud on Google storage. Once you have it in the cloud, then everything is, remember what I said about the Google fiber network? Our fiber behind our firewall is as big as the rest of the internet combined. So you're talking gigabit Ethernet and petabit Ethernet. So you're talking really, really, really fast networking speeds. So it doesn't matter where on the cloud it is, but it needs to be in the cloud. It cannot be on your local machine. So you need to get your data into the cloud. That's the first thing about doing any kind of these kinds of stuff. So yeah, so the type of data that you tend to move back would be your result data, hopefully, and that will tend to be small, and it could be interactive. But you really shouldn't think in terms of moving your data to run one BigQuery query. You should be thinking in terms of keeping your data on the cloud permanently. It's cheap. It's not storing your data on a cloud is cheaper than storing it anywhere else. So you might as well keep it on the cloud. Okay. Another question, can I connect the data between BigQuery and Dataproc? Absolutely, right? Remember that BigQuery is essentially, it's a Python package. Same with Dataproc. Now you can do Spark right in Data Lab. So you can do both, absolutely. That is not a problem at all. No, it's just a Python package, right? So you can do everything else that you would do in Python in conjunction. And as you can see, BigQuery, it's not just some random data structure. You can convert it to a pandas data set. So you can do everything that you can do with pandas. So you can do seaborn plots. You can do anything like that. So it's very well integrated with Python. Cool. Great questions. Any others? Okay. I may not have completely answered this. The interface of data from local machine and from cloud machine, is there any difference? Yeah, we really want your data on the cloud, but you can have your data on a Google Sheet. You could have it on Google Drive. You could have it as plain old CSV files, not just the BigQuery files. But remember that the thing about all of these is they're all on the Google network behind the Google firewall. BigQuery, the whole the idea doesn't work on local data, right? The whole thing is that we're scaling it to hundreds to thousands of machines. If it doesn't work, it doesn't work, right? If you just have it on one machine, you will not get the speed that we're talking about. Okay. So cool. Let's move on. So what we just showed you was BigQuery, and that is great if what you want to do is a SQL statement at scale. Right? So in other words, if you have a declarative thing that you want to do and you want to basically do it over a large data set, BigQuery is your answer. But what if you want to do a while loop, a for loop? You want to do programmatic things, right? You want to basically call some other Python functions on your data, right? In other words, BigQuery is declarative. We need a serverless auto-scaling thing where you can run arbitrary code, not just SQL statements. And that's what Dataflow is. Okay? So I'm going to show you Java here. And the reason I'm showing you Java is because a Python API, which I'll show you in a bit, is an alpha. Right? And because it's an alpha, I'll show you, I'll do a demo using using Java, but it's an alpha now. It'll go in beta probably in a matter of months, and then you'll be able to do everything that I'm showing you here in Java. You'll be able to do it in Python as well. So the basic idea, but the concepts carry through. So let's talk about the concept. The idea behind Dataflow is that you create a pipeline, right? And you say, here, I'm reading from GS, which is Google Storage. I'm reading text from Google Storage. And for every line of that text file, I'm applying filter 1. And then its result, I'm applying the group 1. And then the result of group, I'm applying filter 2 to each item in it, and then applying a transform to each item in it, and then writing those results out to Google Storage again as a text file. Now, all of these things are code that you write. So filter 1 is your Java function. So is group 1. So is filter 2. So is transform 2. So it's your code that you're writing, and you're basically breaking it down into steps as you're processing your data. The really cool thing is that filter 1 is wrapped up in a par-do. Par-do is a parallel do. And what this means is that for every line of that input text file, filter 1 is going to get applied. It's going to get applied in parallel, meaning if this thing requires 800 machines to do, we'll run it on 800 machines. It will get auto-scale, get run. The results will come back into group 1, and then those results will then get filter 2 will get applied again in parallel. But maybe this one is a smaller data set. We don't need 800 machines. So maybe we do this on 30 machines. And then transform 1 happens on those results, and then everything gets written out. So remember, this is again, you're just going to just submit a job, but you're not going to create a cluster. You're just going to submit this pipeline and say, run this for me, and we'll run it on as many machines as we need to get the job done for you in a matter of minutes rather than over an entire weekend, right? So that's the cool thing. The actual API itself is an open source API. It's called, Google's open sourced it. So it's called Apache Beam. The implementation is Dataflow, but you will also have other implementations. For example, Flink is going to be another implementation of Apache Beam. And what Google will do is that we'll compete on the quality of our implementation. We'll say that Dataflow is a better implementation, faster, better auto-scaled, etc. Because again, even though the API is open source, remember that you need a whole bunch of engineering work on the back end to do this auto-scaling and clustering. So we'll provide a good execution environment for it. But at the same time, you're not kind of lock-horned into using Dataflow. You can always take your code out and use Apache Beam and run it somewhere else, wherever you want. Now, this is what the Python API looks like. So here's a Python API for word count minimal, right? So the way it works is that you start with a pipeline, okay? And then I'm saying data frame read, text file source from the input file, which is from Google Storage. And those are all your lines. And those lines, you pipe them through a split function, right? Where you're basically finding, this regular expression, right? And you're basically outputting a Unicode string. And then you're basically saying for each one of those, pair it with the number 1, right? So you basically have the name of the word and the number 1, group it by key, and then basically go ahead and do a sum. And now you basically have the counts of each word, and then you basically map those counts into a string. So for the name of the word and the number of counts, and then you write it out, right? And basically, here's your pipeline. And then when you want to actually go ahead and execute the pipeline, it would look something like this. Where's my? Let's just go here to execute the pipeline. So there's Dataflow. Okay. So you would basically say, I want to, this is the Java one, but no, Python one is very similar. You basically say, here's my staging location. This is my input files. This is where I want my output directory to go, and go ahead and run it for me, right? And basically goes ahead and runs it. And it's completely auto-scaled at that point, and you're not actually starting up a cluster to do this. Okay. Okay. Now, I just showed you the code as it would look if you're processing reading text files as input, writing text files as output. But we can just change the input to be pub/sub, which is a messaging system. So now I'm reading from an input topic, and I'm basically chunking it by 60-minute windows. And it's a sliding windows off. There's also a sliding windows .every, and the default for that is 1 minute. So what this is doing is that it's creating a 60-minute window every minute. So every minute, it's applying this entire pipeline to 60 minutes of data. And then 1 minute later, it comes back and it does it again. And each time, it takes those results and it writes them into pub/sub.io. You could also write them into BigQuery. You could also write them in, you can't write them into text because, again, you're writing it every minute. And on the cloud, a text file cannot be appended to. So typically, you will write it into pub/sub or you'll write it into BigQuery. And then if you want it, then you can export a BigQuery table later on at the end of it, or a pub/sub topic later on at the end of it into a file if you want it. But the point being that you basically have a data pipeline, and you can basically change the input from text to pub/sub, and all of a sudden, you're basically processing streaming data, right? There's no other difference. You can process both streaming data and batch data. So in fact, you can mix the two up. So the whole idea behind Dataflow is that we can do ingesting of data because it can do real-time data. You can do transformations of data because you can do them in parallel. And you can load the data into BigQuery, right? Or into a pub/sub topic. So you can do ingest, transform, load. So pretty much you want to process data. You want to process it with an auto-scaling pipeline. Dataflow is your answer. And remember, again, it's completely auto-scale. It's completely serverless. So that's why we say at Google, we don't use MapReduce anymore. Every job at Google, right, is essentially either a BigQuery job if it's every big data job at Google. So either a BigQuery job if it's declarative, if it can be expressed as a SQL query. Internally, it's called Dremel. And Dremel is used very, very widely within Google. Whenever you can express it as a SQL statement, use BigQuery. But if it's not a SQL statement, or if you need to process real-time data, or you need to do ingesting of data or loading of data into BigQuery, that's where Dataflow comes in. So this combination of Dataflow and BigQuery is very, very, very powerful. And this is what we mean by our second generation of our big data stack. And that's what we're asking people to use, because it's completely serverless. It costs you exactly the same. So why would you want to wait a weekend to get your results if you can get them in seconds? So seconds in the case of BigQuery, minutes in the case of Dataflow, because the way Dataflow works is that it starts out with 3 machines and then says, oh, 3 machines are getting swamped. So let me scale up to like 10 machines and then 30 machines, etc. So because of that ramp up phase, and because there are multiple steps involved, typically a Dataflow job takes on the order of 2 to 5 minutes, right? So that's basically what you're looking at. You're looking at, about 7 to 10 seconds in the case of BigQuery, or 2 to 5 minutes in the case of Dataflow. So here's my demo. So here, I'm going to actually do something here. I'm going to window the data. So sure, I have a departure delay. I have the distance. But the other thing that I want to do is that we say, well, are flights tending to will flights at this airport tend to be late at this hour? For example, if you're in New York at JFK Airport, 5 o'clock in the evening, every evening, flights take a long time to take off. But then that's built into the airline schedules, right? The airline knows that at 5 o'clock on every weekday, it's going to be an hour to take off anyway. So their arrival time will be set appropriately. So we need to know what the average departure delay is, so we can see, is this 15-minute delay that we have, is it unusual or is it normal, right? So we want to know the average departure delay. We also want to know in real time, the place that we are landing to, do they have weather? Do they have only one runway open, etc.? So we want to know the average arrival delay at the airport at the present time. And I hope you guys see the difference here. One of them is a historical thing, the average departure delay. The other is a real-time thing, the average arrival delay at the present time. And that's basically going to be a training data set that we can use to do machine learning on, right? So to basically do a prediction. And that's basically what this code looks like. Okay. So here, I'll basically go ahead and show you. So to create the training data set, I'll basically be creating a pipeline. Okay, and again, this is Java, so I won't spend too much time on it. I'll basically read lines from my flights database, parse it into a bunch of flight objects, and for each object, I'll basically go ahead and get for every airport every hour. So basically, now from the airport to from this hour, here's the departure delay, and here's so the total departure delay, and then I can basically get the average mean per key, and then I write that out. That's my departure delays. And then I can basically get my average delay and do this on the arrival side, right? And basically write these things out. So this is just my data pipeline, and I can then go ahead and simply execute this pipeline by running that thing I showed you, the run on cloud, right? Which essentially goes ahead and executes that create training data set. And it does it on a bunch of CSV files in Google Cloud. I mean, we can also read out of BigQuery, but we can read out of plain old CSV files in Google Cloud Storage itself. So that's what I'm doing, and I'm writing my output into another cloud storage. So before I move on to machine learning, do we have any questions about Dataflow? So again, you should have gotten the PDF of my talk, and all these links are there. So feel free to basically go ahead and look at those links in more detail. So any questions? Okay, in order to code on this, it looks like a lot of Google-specific API needs to be used. Not really. That entire API is Apache Beam, right? It's basically an Apache Beam open source API. The execution of it is going to be Dataflow, but you will be using an open source API. So both on the Python side and on the Java side, it's an open source API that you're using. And right now, Dataflow is the only full execution engine, but Apache Flink is coming along. So you will have another execution engine, at least, to do this. Next question. Is there a way for a well-written, multi-threaded program to use all this power of Google Cloud? So if what you're thinking about is Spark, then yes, Dataproc will let you execute Spark jobs. So you can use a Dataproc cluster and Spark to do this. But if you're talking about a generic multi-threaded program, then what I would suggest would be that you go ahead and you use Google Compute Engine, which will basically give you a VM. But it doesn't really give you the power of the cloud because it doesn't give you this elastic scalability. Because we're not talking about just multi-thread. We're talking distributed programming. Okay. Next question. Do I have to set up an instance to use Data Lab, or is it also serverless? So Data Lab, okay, there are a couple of things. What I just showed you was a Docker container, right? It's a Docker container. And you can take that Docker container, and I was running it on my local Mac. So you can just run it on your local machine, and whichever one, as long as it can run Docker, you can run Data Lab. So that's one option. The other option is to go get a Compute Engine instance and run the Docker container there, right? But Data Lab is not serverless. Remember, the reason you need serverless is if you need this auto-scaling business, right? So Data Lab is a Docker container, and you need to pick the machine that you're going to be running it on. And the version of Data Lab that I showed you is actually a new version. If you go to the current beta version that you might see elsewhere, that actually picks your Compute Engine instance for you. Okay, but the Docker container is the one that you should be using. So use a Docker container one. It's a lot easier. So the third thing that I want to talk about is machine learning, right? Machine learning and TensorFlow. And the reason we want to talk about machine learning is so we have one set of transformations around the big data side, which is this whole idea of completely serverless and auto-scale architectures. Machine learning is this other transformation that's been happening at Google. So in the last 2 to 3 years, the uses of machine learning and TensorFlow in particular went from essentially 0 to in the thousands. There are thousands of projects. And you've been seeing that all over Google products, right? Many of you used to use Picasa, and the way Picasa worked was that everything was very rule-based, right? You would create a folder, you would give it a name, you would say this is what it is, you would put a tag, and we would basically give you those tags back. But Picasa's been retired. It's been replaced by Google Photos, right? And many of you may have used Google Photos, and there it's essentially auto-classified. Right? And I think we all agree that it works pretty well in terms of clustering people, in terms of clustering places, in terms I can basically go to my Google Photos, and in fact, I was wearing a T-shirt that said Ladakh, and someone said, "So where is Ladakh?" I said, "Ladakh is on the Tibetan plateau. We went there like 6 years ago. Here, let me take my Google Photos," and I typed in Ladakh, and I got all my pictures from 6 years ago. I had not tagged it, but it came up. Right? So that's basically what machine learning is about. Machine learning is about not programming a computer by giving it an explicit set of rules. Instead, you show it a whole bunch of data, and it kind of figures it out over time. Right? So nobody went to Google Photos and taught it what Ladakh looked like. Right? It figured it out based on a few people somewhere, some nice souls, took some pictures in Ladakh and tagged it as Ladakh, or had GPS coordinates that said Ladakh, right? And from that, it was able to figure out from my photographs, it had no GPS. I was using an SLR camera that didn't have GPS on it, but was able to figure out that those were from Ladakh, right? So that's essentially what machine learning is about. But so why would you want to do machine learning on the cloud? The reason you want to do machine learning on the cloud is that if you want high accuracy, I mean, that's what you want, right? You want extremely accurate machine learning models. You need a really, really large data set, Okay, your data set needs to be, oftentimes in the millions, right? Google Photos was trained on millions of images, right? Google Translate was trained on millions of documents. So you're talking about large amounts of data. You need really large data sets. But the reason it works very well on such large data sets is because we can afford to create a really complex neural network, right? A neural network with lots and lots of layers, lots and lots of nodes. This is called a deep neural network. If you have a neural network that's very large and a data set that's very large, then of course your compute problem is also tremendous. And that's where the Google Cloud comes in, right? If you want to be able to do this very large data set, very large neural networks at very high accuracy, then you need specialized hardware, TensorFlow processing units. You need it to be auto-scaled to many distributed machines. It doesn't work to just do it on a cluster of a few machines. You really want to scale this thing out. So that's kind of why you want to do machine learning on the cloud. And so let me just show you a couple of demos. So when you talk about machine learning, people think TensorFlow, but the first place to start with machine learning is with already developed models, right? So already developed models may be for doing translation. So for example, there's a Google Translate API. You can give it a Chinese string and we'll give you back an English string, right? So we'll just do the translation for you. I mean, it's essentially the same translation that's built into our products. Similarly, there's a Google Vision API. You put an image up on the Google Cloud and you say, please run the Vision API for me. Tell me what's in the image. That's called label detection. Or tell me if there are people in this image and where the faces are. That's called face detection. Again, face detection, not face identification, right? So we don't tell you who it is, but we tell you that there is a face and here's a rectangle where the face is. You can do optical character recognition. So you can upload an image and say, tell me the text that's in this image, right? You can do safe search, right? So for example, you can load up an image and say, this image, does it have any pornographic content, for example, right? So for example, if you have an application where you're asking people to submit images and you want to make sure that the images that they submit are not unsafe, you can use the Google Vision API to do it. Similarly, like what Google Photos does, landmark detection, that is built into the Vision API. So you can say, where was this photo taken, for example, and we will basically help you do that. We will also do logo detection. So this is a huge thing. If you're a fashion firm and you want to see if somebody's out there selling a handbag with your logo on it, right? You can basically trawl thousands of images for looking for your logo. So that's a Vision API, and it's very straightforward. All these APIs are simply a REST call. Oh, I have a question. Okay. Question, what would I miss if I use AWS, install the Spark and pip and other Python packages instead of Google Cloud for machine learning? Skykit is also be configured, right? What you would miss would be some of the auto-scaling things. You would miss the ability of, what I'm going to come and talk about, of doing machine learning, building on top of Google rather than replacing it, right? So for example, if you're going to be doing image classification, there are two ways to do it. You can do image classification by loading up a bunch of your images and getting a model. But how many images are you going to have? Maybe you have 10,000 images, maybe you have 50,000 images. That's kind of the scale that you might have. What you might want to do instead is what's called transfer learning. This idea that you take a Google learned machine, our Vision API, our image model, right? You take the first 18 layers of our image model, which has been trained on millions of images, and then you train only the last layer on your images, right? So on your 50,000 images. So there are advantages to using the Google Cloud. But again, we don't want to, the reason that we open source TensorFlow is because we don't want to tie people in. We want to say that the Google Cloud is the best place to run it. And if you try the Google Cloud, you will love it so much that you will want to stay. But we're not going to force anybody to do that, right? So TensorFlow is open source. And if you want to run it on AWS, you absolutely can, right? There's nothing stopping you from doing it. But the quality of the models that you will create on the Google Cloud are going to be better simply because you can build on top of Google's own stuff rather than doing it from scratch. I hope that answered your question. So again, we're talking about also machine learning, not just using Spark, but using TensorFlow. If you're using Spark, then yeah, you can use AWS, and it should be pretty identical, right? Whether you use Microsoft or AWS or no, because essentially you're doing things from scratch. Okay, but I hope that when you do your machine learning, you're not doing it from scratch, right? You're instead, like with any other software, right? If you're building software in Python, you're not going to be writing you're not going to be writing packages from scratch. You're going to be looking at packages that have already been built and building on top of those packages. Machine learning is no different, right? Again, I think for people who are new to it, you may think that, oh, I'll just come in and use TensorFlow from scratch. But for those of us who've done it for a while, we know that you will get a lot better results. You will develop a lot faster if you can build on top of already existing models. So it's like any other software, right? So machine learning is new to you now, and you may say, and all of the examples and tutorials and everything show you how to do it from scratch. But you will get much better results if you build on top of existing models. So that's basically it. Okay. The machine learning APIs, are they available for us to tweak? Yes, TensorFlow is open source software. So you are absolutely allowed to go ahead and grab it. So TensorFlow.org, right? It is open source. We've open sourced the machine learning library. What we have not open sourced is our models, right? So the Vision API model, the Translate API model, or the Speech API model, we haven't open sourced, right? So we've open sourced the software. We haven't open sourced our data, right? Or the models that we built on our data. And the quality of our models is highly dependent on the amount of data that we have. And that's basically our competitive advantage, if that makes sense. So as a quick demo, let me just go ahead and show you what this looks like. So this is this is a demo of the Speech API, and all that this is that this is a web page. And in this web page, what the person has done is that they have gone ahead and are making REST API calls to the Speech API. So they've linked up to the microphone, and when I talk, they're basically taking the sound from my microphone, and they're sending that sound waveform to the Google Cloud. And the Speech API is sending back text, and they're showing that text in the text box. As you can see, it's pretty darn good, right? And this is you can look, again, this is a simple demo, and it's linked from the PDF. And if you look at the page source here, you would basically see a call to the Speech API. Questions? Okay. So you mentioned that TensorFlow is open source. Can developers extend TensorFlow with additional algorithms? Absolutely, you can, right? So again, TensorFlow.org, right? So that is it, and there is the API, right? And you can basically go ahead and you can download TensorFlow, pip install TensorFlow, etc. There is a Python API, and part of TensorFlow is like a contrib directory. So there's a whole bunch of contributed stuff already. Another thing is TensorFlow examples on GitHub. And that's another place where people contribute. So here's a GitHub account, right? And so people contribute how to do nearest neighbor, linear regression, logistic regression, neural networks, right? And how to do residual neural networks, AlexNet, natural language processing, all of these things in TensorFlow. Okay. Is TensorFlow available? TensorFlow is just a Python package, right? So, but it uses a C++ engine. But yeah, so you can pip install TensorFlow and use it locally. It doesn't have to be on the cloud. Okay. Yeah, you can use TensorFlow locally. It does not have to be on the cloud, not at all. So that's something that people do. They try it on a small data set first. You can do it in Data Lab, right, on your local machine. That's the way I would recommend you do it, rather than installing TensorFlow and C++ and everything yourself. Just use the Data Lab container. It already has TensorFlow installed. Run it locally, right? Run the Data Lab container locally and try out TensorFlow. And then once you're happy with how it works, then basically run it anywhere, right? But even with TensorFlow, you can run the open source code, TensorFlow, right? But the better thing would be to basically do Cloud ML. So Cloud ML is basically TensorFlow that is distributed, that's auto-scaled, right? That is, so once you start getting a large data set, once you start doing experimentation on machine learning, so you will try to do machine learning models of different sizes, different things, different hyperparameters, etc., and you want to choose the best model, you'll be doing it many times, right? You might want to do it with Cloud ML. Now, things that we see are, if you do it with just TensorFlow without the auto-scaling, it might take you about 72 hours. But if you do it with Cloud ML, it might take you an hour, right? So that's the kind of speed up that you're talking about. And again, as I've told you before, the cost is the same. Whether when you auto-scale, the cost is the same. You can either spend 72 hours doing it, or you can spend 1 hour doing it, right? So it's basically, it's all about getting faster results. It's about fixing your errors faster. So as a demo here, so I used Dataflow to create this training data set, and then I want to create this likelihood that the flight arrives greater than 10 minutes late. That too is on GitHub, TF train local. So this is how that looks. So I'll show you both. So here's my real-time data. So here's tftrain.py. Oh, I see. It's in 8. tftrain.py. So the way it works is you basically get your training files, and then the way TensorFlow works is that you first build a training, you get the training data, right? And in my training data, I have a label, I have a departure delay, I have the taxi out, I have the distance, I have the average departure delay and the average arrival delay, all from the CSV file, right? And then I basically say, I want to go ahead and do a I want to batch this thing in batch size with the number of threads, right? So every time this get training data is called, one part of this training data, one batch, right? And the batch size here, in my case, my batch size is 10,000. So 10,000 examples get returned. Remember, my data set is like 6 million points, right? So 10,000 of those get returned, okay? And then I will also go ahead and create the graph. And my graph basically says, I'm going to create, right, a placeholder for the number of predictors, a placeholder for the number of outputs. And then I have my weights, I have my biases, both of which are Gaussian variables, right? And I'm basically going to create them, right, with, let's see, I had hidden nodes. Do I have it here? Yeah. So I have a 4-layer network, right? So I have 50 hidden nodes in one layer, 10 hidden nodes in one layer, 5 inputs, and 1 output. So that's basically my neural network. And then I basically create the sets of weights, sets of biases, and then create my model where my activation function is a tan hyperbolic, and my final output function is a sigmoid because I want to do classification. And then I have a dropout layer in between because those tend to work well. And then that's pretty much, and then I have a ReLU for the dropout layer, right? So then I basically go ahead and I do my training. So I basically get my data, I optimize it, I minimize the cost. That's basically what I want to do. I start my training, And then for each batch, I run the training step, passing in the feature data, passing in the labels data. And at the end of it, I basically go ahead and I save the model. And then whenever I want to do my prediction, right, this is what my prediction looks like, right? So whenever I want to do my, that's my eval. Let's see, does it have a prediction example? Okay, I don't have it. Okay. The prediction is essentially going ahead and calling, actually this would help. So the prediction essentially involves doing this exact same, right? So you basically retrieve it from the model, and you basically go ahead and you call the prediction function. So, and the result of this, because I've trained it on data that's more than 15 minutes late, is a probability that a flight is more than 15 minutes late. And then I can threshold it, as with Spark, on 0.7 to make my decision. So that's basically how you do TensorFlow. And then again, as I said, you could do TensorFlow, which is an open source thing. But the better way to do it would be to use CloudML, which is auto-scaled, and it will run it for you. But again, there's nobody forcing you to use CloudML. If you're just playing around with small data sets, you could do it with just the open source TensorFlow package. Okay, so this is typically the way a typical data pipeline that is auto-scaled and serverless, this is what it looks like. You get some older data that you store on cloud storage. New real-time data as it comes in, it goes into an event stream, and that streaming pipeline and the batch data are both processed using Dataflow, and then the data gets written out into BigQuery and then stored for analysis. And then if you want to do machine learning on it, you read from that BigQuery data, you do your selects, you do your averages, etc. And then you can basically go ahead and do your CloudML. You can use Data Lab to do your interactive data exploration. And because it's BigQuery, it's an easy way for people to do your analysis. You can basically go ahead and just give people access to your BigQuery table so they can run their own queries on it. You can also save results into Google Sheets and share those Google Sheets. So this is basically the typical pipeline of how you would do an auto-scale serverless data pipeline that goes all the way to machine learning. Okay. And with that, I'll take any other questions that you have. Any other questions? Where are the models stored? It's up to you. You get to choose where you want to save the models. So in my case, I'll show you where tftrain.py is. In my tftrain.py, I set saver.save, right? And the model file, and my model file was, I saved it here, right? In Google Cloud Storage. But you could also save it to your local file where you're running it. So it would be on your local machine, right? If you wanted to save it to your local machine. So it's wherever you put that saver.save. Actually, let me see. Oh no, actually, I take that back. My model file is no, is temp train model. So I'm saving it on my local machine, and then I'm copying it to the Google Cloud. So in this case, it's stored both locally and on the cloud. What are the recent notable advancements in ML speech applications? How would you rate the current state of the art? And what's holding it back from maturing further? Basically, I think the recent advancements have been primarily around recurrent neural networks. This idea of being able to analyze sequences of text. And I don't know whether you've tried out speech recently, but speech has come a long way, right? I mean, I remember I broke my arm maybe 7 or 8 years ago, and I was using the speech, like dragon speech at the time. And it was not good at all, right? It could not understand my Indian accent. But now it's, I just showed you a demo, and it was not, it was not a problem at all, right? And pretty much like 30% of searches on Android happen through search. And it wouldn't happen through search if it weren't accurate. In fact, I prefer to do a voice search now rather than use swipe or anything like that, because it tends to be more accurate. It doesn't tend to have these autocorrects kind of things. So the only thing that's holding it back is the size of the data set. So very common words, common languages, etc., it's not a problem. But once you get into more esoteric languages, things that are spoken by only 5 million people in the world, or you get into jargon, right? That's where the speech APIs, they don't have enough of a training sample. And when you don't have enough of a training sample, that's where they have problems. But it's come a long way. I guess that's all. Okay, thank you very much. Okay. And this will get recorded, and I'll send a video off to the Python group, and you should have a link to it. So you should also have gotten the link to PDFs themselves. Okay, thank you very much. Bye-bye.